Hello, everybody. Welcome to the third week lecture. So today we're going to be talking about we're going to start diving into a little bit more geometric concepts, not just logic and proof. So logic and proof is something that is wider than geometry, but we're going to be using it a lot in geometry. So from here, I'm going to talk about, I'm going to kind of review logic and proof real quick, and then we'll start getting into geometry a little bit more, the shapes and figures and stuff like that. So let's start with the proof that I gave you on your homework, and it also was at the end of the video last week, where I proved to you that 2 is equal to 1. Now, since in my proof I let A equal B, so that would have been a postulate, A is equal to B. That is my premise that I'm starting out with, okay? So I had to assume that A equals B. A might not equal B, but I am assuming that that's true. Okay, so then we worked our way down, and then we eventually got to 2 equals 1 using legitimate, factual, algebraic properties and methods. Now, 2 does not equal 1, and we all know that. So that means that there is a problem with the proof. Well, I'm going to show you the problem really quickly. The problem is that in our premise right here, we set ourselves up for failure later on. So later on, we have this part right here. Now, that part is since A minus B, since A equals B, and we subtracted B from A, we should get a number. There should be a number there that we actually know. So I'm going to use what's called the substitution property, which we'll talk about later. So I have A minus B. This is equal to A minus A. It's also equal to B minus B because of substitution property. So what I did was, since A equals B, I just plugged A in for B. A minus A would equal 0. Any number minus itself is 0. So what happened here? Well, we divided by 0. I mean, I would hope by now that you would understand that dividing by 0 gives us some problems. So some people say that we can't divide by 0. Some people say that we can divide by 0, but it just gives us complicated results. I mean, I'm not going to get into that argument, but I will say that dividing by 0 will give us will allow us to do some crazy proofs. So I could have done this with 4 is equal to 2. I could have done this with 3 is equal to 1. I mean, I could have done this with a lot of different numbers and set it up and manipulated it to a way that you would have gotten divided by, using that divide by 0 concept, and then prove that something that wasn't true is true. So what I want you to take from this is a proof. I mean, this is logical. I used deductive reasoning. I started out with an inductive reason, which was A equals B, so I assumed that to be true, and I used deductive reasoning down to where I proved that 2 is equal to 1. So what I want you to take from this, I'm going to write this in a big square, is that, let's wait for it to, what I want you to take from this is that proof does not equal truth. So whenever you're having a conversation with someone and you say something and they're like, well, prove it. Well, what is proving it going to do? Is proof going to show that it's true, or is it just going to show that you have reasoned it from something else that you know? Proving it means that you have shown reason that it's true. Now, if we would have gone back up in here and we would have started with A equals B, and our assumption wouldn't have led us into a problem. So last week we talked about assuming that a lady that you know is pregnant whenever she's not pregnant. So I assume that she's pregnant, and then I go up to her and I say, hey, how far along are you? And then she slaps me. That is where we went last week. So from here, I want you to, that's what I want you to notice, is that our assumption led us to a problem later on. Now, that is how we can show that things are true. If our assumption is true, if the assumption is true, and we use deductive reasoning and get down to the conclusion we can say is true. But that proof is the reasoning that you got to your conclusion. Okay, so it has to start with the truth, and then you reason from it into the truth. Okay, so I hope that that helps. But that's one thing that I want you to take from here, is that proof does not equal truth. All right, so from here, we're actually going to go on. I'm going to leave it in blue. We're actually going to go on to figures. We're going to start talking about shape to an extent. Next week, whenever we start, we're going to begin chapter 2 next week. We're going to talk about lines and angles, and then different postulates in lines and angles, and then maybe do a few proofs. But for now, I want you to understand that what a congruent figure is. So congruent figures, the definition of congruent figures is figures that are the same shape and different size. So let's talk about like a triangle. So here's an example. Let's say I have two triangles. And let me draw both of them. I'm actually going to duplicate so they get this right. And these two triangles have the same angles. I'm going to draw two lines here denoting that those two angles are different. They have all the same angles. They have all the same measurements and size, and they're also the same shape. So these are triangles. The shape is the triangle, and then their size is the measurement of the lines and the angles, which we'll get into that. Since these two figures are the same size and shape, they are congruent. Okay, so that's what it means to be congruent, is that they are the same size and same shape. So the next thing we're going to go to is similar figures. So similar figures are a little different. Just because things are similar doesn't make them the same. So that's the reason why they use the word similar. Similar, the definition of similar figures is figures that are the same shape but different sizes. Okay, so like before, we had a triangle, and they were the same shape and the same size. Okay, well, let's look at a triangle. Let's see here. Draw everything out as best as I can. I'm going to see if I can duplicate it and then make it smaller. And then, yeah, there we go. All right, so these are the same shape, but they're different sizes. So that means that they are similar figures. So that's the difference between similar figures and congruent figures. So these are similar. Now I'm going to talk about the different transformations that we can perform on a figure that allows them to maintain congruency or to maintain similarity. So these transformations, I'm going to list them out. Transformations. Make that a little bit more. These transformations are, let's say we'll start with rotation. Go with all the big R's first. Rotation, reflection, translation, and dilation. Now, these are the different ways that we can transform a figure. Now, performing these four, the figure will either be congruent or it will be similar. Now, I'm going to show you which ones will make that will leave the two shapes similar, and then I'll show you the two shapes that are congruent. So we're actually going to go to GeoGebra. So we had a video earlier on GeoGebra, so I'm not going to go into what it is, but I'm going to go ahead and construct a polygon. And in that video, okay, I don't know what happened there. In that video, now we're going to perform a rotation, and we're going to perform a rotation on this object. Now I'm going to do it a little, I'm going to show that we can get a full rotation. Let's cancel. Let's go there, do that, slider. And I'm going to show the exact same rotation that we did in the video before. I'm going to rotate it 360 degrees, and we're going to increment it by 1. Now up at the top here, it has a line with 2 dots. That tool I'm going to do rotate around a point. So it wants me to click on the figure, click on what I want to rotate it around, and I'm going to plug in the letter D because that is up here at the top, D equals 1. That is what I'm going to type in. So this is just to show you rotation real quickly. So I'm going to animate. This is a rotation. Now if you notice, after it rotates, it'll come back around, so that it's rotating completely around. When it gets back to the top, it'll actually, you can see that the 2 figures are the same. So whenever I pause it, it looks like 2 different figures. So like right here, these are 2 different figures, and they are separate from each other. That's why they put these little tick marks with the A. That just shows that there's 2 different figures. So if you notice that whenever we get back to 0, they sit right on top of each other and they're the same shape and the same size. That's what a rotation is. Okay, so that's what I want you to take from that, is that a rotation will maintain congruency. So I'm going to go ahead and just start the program over again. So our next one was reflection. So we did rotation and we checked it off. Rotation maintains congruency. So now we're going to look at a reflection. All right, so I'm going to do the same figure. And I'm going to plot the points. Same triangle, make a polygon out of it. There, 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 and there. And we're going to reflect it. I'm going to create a line real quick. So the line that I'm going to do is x equals 0. For you algebra people, you're going to understand that. All right, so now we're going to reflect it about a line. Select the object, then I'm going to reflect the line. And you see that it reflected. You can also see that these 2 shapes are the same. Like if we look at the area, it is 3. The bottom is 3 apart, 3 apart. They have the same sides and the same shape. So reflection, let's go back here. Reflection does maintain congruency. I'm going to go ahead and exit out of this. We're going to do a transformation. Let's do the same figure. Delete that point. I don't know why it keeps doing that. All right, let's delete that point. Make our polygon. Okay, so we're going to translate by a vector. Okay, so select the object, then we must select that, and then now I'm going to select here. I'm going to create a vector real quick. A vector. There. Let's do that backwards. Let's delete that and create one from there to there. So translation is a movement. So we're going to slide it over to here. The vector is going to show us whenever I click on this, translate by vector, I'm going to click on that, then I'm going to click on my vector, and it shows it being slid over. So translation is a shape being slid in either direction by a vector, but you all don't need to know what a vector is. So it's slid 2 units to the left. That's what happened here, is I created a vector of 2 units, and then I slid it over 2. This actually shows congruency. So let's go back to, let's go back here. Translation does maintain congruency. So now we're going to dilate the same image. I'm going to go ahead, start over, and I'm going to move it down here to show dilation. Create the same triangle. And we're going to dilate this triangle from the point here. And all right, so dilate from a point. I'm gonna create a slider on this one and animate it, because why not? And we're gonna do 0 to 20. And we're gonna do increments of 0.01. Yeah. All right, now start it at there, dilate from a point, there. Dilation factor, we're going to type in D because of our slider. Okay, I don't know where that point came from, but now if I go up here and animate my slider, you can see animate my slider. Might have made it a little bit too big, but I don't need to animate. So if you see what's happening here, the triangle is getting bigger and smaller. That's what dilation means in mathematics and in nursing, but we won't go into the type of dilation that you'll be learning about. Okay, so this right here is showing that the shape is getting bigger and smaller. That's what a dilation is. It dilates by a factor of what, well, in this case is D, so I'll get it right on 2. Right there. So if you notice, the area of the triangle actually doubled. So the factor to which it dilates is a matter of 2. I don't expect you to know how to dilate right now anyway. We might learn that later on in the year. I don't expect you to know how to dilate, but I want you to understand that dilation does not maintain congruency. These two figures are the same size, but they are not the same shape. All right, so whenever I go back to here, I'm gonna write it in green. I'm gonna put a big X. And I don't like that X, so I'm going to do a dark blue. Okay, so dilation does not maintain congruency, but the two shapes are similar. So with that being said, I'm going to write this off. This means congruent. I'll write this in blue just like I had it. This means similar. Yep. So what I want you to take from today is what congruent figures are, what similar figures are, and then what transformations maintains congruency and what ones don't but maintain similarity. Okay. So that's all I have today. I'll see you in the next video. Thank you.